Welcome to Module 4, Part 2. So, in the last part, we had discussed about the biasing of the Jfet. So, we applied the gate to source voltage, and we increased the drain to source voltage, and we found that how the current increases. So, when the gate to source voltage is increased in the reverse bias condition. So, here we could see. So, when VGS is 0, how the current is high. So this is the case when VGS is 0. So this ID over here for the case 1 and ID over here for the case T. Here you can see, so when we increase the VGS voltage, the depletion region widens, and as a result the resistance of the N channel increases. So when the depletion region increases, the resistance increases, and the drain current is blocked by this particular depletion region, as a result of which the drain current decreases. So here you can see ID1 is greater than your ID2, and this is greater than your ID3, the third key ID3. So in the third case over here, this is the ID, we'll consider this as ID3. So in this case, the depletion region has completely blocked the channel. The resistance is very high, and there is no flow of current into this particular channel. So ID1 is greater than ID2, which is greater than ID3. So the depletion region over here acts as a channel, acts as resistance for the flow of the current. So the channel is essentially a resistor, and the channel resistance increases when the depletion region widens. Next, we'll consider the case when the gate to source voltage is kept constant, when VGS is kept constant, and VDS is increased. So similar to the previous case, we have the terminals. So over here we'll just consider the cross-section view of the N channel transistor. So we have the P terminals, and then we have the drain and the source terminal. So this is connected to VDS, and then we have the gate terminals. So gate terminal over this side and this side are interconnected, and then we connect the reverse bias condition. This is your VGS. So VGS is made 0. VGS is equal to 0. So in this case, what happens? So when we increase the VDS voltage, so assume that we have increased this VDS voltage. So initially, when VDS voltage is increased, there is a depletion region formed across the P-type material. So on either side of the P-type material, the depletion region will be formed. VGS is 0. So when VDS is increased, the depletion region is formed, but it will not block the flow of the current. So the current will be linear. The flow of current will be linear when we increase your VDS voltage. Next, we further increase this VDS voltage. So VGS voltage is kept constant. VGS voltage is not varied now. Only the VDS voltage is varied. So when we further increase this VDS voltage, so there is a slight increase in the depletion region. It widens at the drain side, and it is narrower at the source side. So it widens into the channel. The depletion region widens into the channel. It slightly blocks the flow of the current. There is no free flow of current into the channel, just like the previous case where there was a free flow of current. Now here it is slightly blocked. The resistance has increased, so the current flow also slightly become constant as compared to the previous case. So initially it was linearly increases, then it deviates, and it is almost becoming constant. So at this particular condition. Now the third case will take where we further increase the VDS voltage. So when we further increase the VDS voltage, so the current is completely blocked. There is no flow of current into the channel over here. So just like the previous case, the current there is no flow of current, or the current decreases. So here the current remains constant. So the current remains constant. There is no decrease in the current as such. So the current remains constant. The depletion region has completely blocked the flow of current into the channel. The depletion region exhibits very high resistance to the flow of current. So this is the case when VGS is still 0, but we have increased the VDS greater than the previous case. So here the current is constant at this particular region. So this region is called the active region. Whereas this particular region over here, when your VDS is less, it is called the Omnic region. So here you can clearly see in this particular graph. So initially when the VDS is increased, so the ID current will also increase. This is the first case where VDS is increased, but VGS is 0. Then this is the point from point A to B. This for the first case. This is for the first case. This region is called the Omnic region, where the current is linearly increases. Then from region from B to C, this is the saturation region or the active region. This is for the second case. This is for the second case where VGS is still 0, VDS is further increased. There is a depletion region which is being formed. Here you can see there is a depletion region which is being formed. So the current is almost becoming constant. And then the third case, so this is the second case over here where there is a curve. Then the third case when VGS is still 0, and then the current ID is constant. So this is the saturation region over here, or the active region, or the saturation region, where the current becomes constant. So this is the third case where we have further increased the VDS, but VGS is still maintained to 0. Now for VGS equals to 0, when VGS equals to 0, the value of VDS over here, so we have the VDS over here. So for VGS is equal to 0, the value of VDS at which the ID becomes essentially constant at point B here, at point B, at this point. So the ID becomes essentially constant is called as a pinch of voltage. So here you can see it's a pinch of voltage. For VGS equals to 0, it's the value of a VDS. The value of VDS at which the ID becomes constant is called as a pinch of voltage. So that voltage, or that VDS voltage is called as a pinch of voltage. Then beyond this, what happens when we further increase your VDS voltage? Beyond this, when we further increase the VDS voltage, so there is a breakdown. So the transistor heats up, and then it moves into the breakdown region, and the device is damaged. So that VDS voltage, the voltage at which the breakdown occurs, is called as the breakdown voltage. So here we have the breakdown voltage. Beyond this, the device is damaged. It heats up and the device gets damaged. So this region is called the breakdown region. So region between the B and C is called the active region or the saturation region. Below this B, when VDS is low and ID is clearly increasing, so that particular region is called the Omnic region. So this is a case when we increase the VDS by keeping the VGS voltage constant. Thank you.